One of the most common ionization sources that is used in mass spectrometry is electron ionization or electron impact ionization. You'll see it written both ways, but both of them abbreviate with EIMS, electron ionization mass spectrometry. Now this has several parts, and so we'll walk through each part and kind of how it works to form ions. Okay, so the first thing we need to do is we need to have an analyte coming in. Okay, this is a gas phase. It's already in the gas phase, which makes this a really easy interface to use with a gas chromatograph. So we already have gas phase analytes coming in. And I'm going to label these as M for just our molecule. Okay. So our little M comes in, and we now come in to an area that again is under pressure, under vacuum. So under low pressure or vacuum, okay? And we're going to basically pass this molecule through a beam of electrons. So how do we get a beam of electrons? So we need something that's going to generate electrons, and we'll use a little filament for this. Okay, it's a little spiral filament. And this filament is going to generate electrons. Now, when it generates electrons, the electrons go in every which direction, and so we're going to need something to form them into a beam. So we'll use a plate that has a positive charge on it. And so in this case, this little charged plate. So now the electrons are going to be drawn towards the positive charge, and so we get them kind of in a beam moving down towards the charged plate. Okay. So as this molecule passes through the electron beam, what happens? Okay. Now the charge on the plate is going to accelerate the electron volts, and we're going to accelerate the electrons. And we're going to accelerate the electrons at 70 eV, where 1 eV, that's an electron volt, is 96.5 kilojoules per mole. Okay, there's a lot of energy going on here. So when those energetic electrons interact with our molecule, it might be tempting to think that this 70 electron volt electron is just going to be absorbed by the molecule, and you're going to end up with a negatively charged molecule. But the reality is this is too much energy for the molecule to just grab onto it and pull it into its valence shell of electrons. So instead what happens is at the point of collision, you get an energy transfer. And in this energy transfer, we end up with the molecule losing an electron. Okay, so this might just be about maybe 0.1 eV. So this is a kind of an ejected electron, which leaves our molecule as a radical with a positive charge because it's down 1 electron. Okay, not 2, so it now has to be a radical. And then the electron that collided with it goes careening off still. We get another electron, and this is perhaps about 55 eV. So there's been a good loss of energy that's required to eject the low energy electron. So this one comes off at low energy. This one comes off still at pretty high energy after the collision. Now this is a really inefficient thing, okay? So only about 0.01% of our molecules are going to actually undergo this collision and become ions. Okay, but when we do this, we do actually have enough to observe this. It's simply a probability thing because we're putting in enough of our molecule. Now, while we've used some of the energy from the high energy electron to end up knocking this electron out, we might still be left with enough internal energy for fragmentation. Okay, so it might have enough internal energy to break some bonds and fragment. And we can think of this as it's just kind of falling apart into its pieces. We'll look at a little bit in a later video how how to predict how these molecules are going to fall apart and predict what kind of ions we'll see as they do fall apart and fragment. But one of the really big perks of this electron ionization is that because the energy of the electron beam is controlled, this energy transfer upon collision and the kind of fragmentation that you get from the molecule at the end is very predictable and very reproducible. And so that's going to be a real advantage for this particular method. Now, when you are ionizing and you also get fragmentation, we call this kind of ionization a hard ionization. So hard ionization equals ionization plus fragmentation occurring. So we get both aspects. Now, just to kind of return to our diagram and finish it out, because right now, we've had our M come through. We now get some ions that are M dot plus, right? And these aren't going to be pulled towards the charged plate because they're oppositely charged. And so now we can kind of control getting these to the mass analyzer. We're going to put a positively charged repeller here. That's going to direct us to some ion focusing optics, some ion focusing plates. And so as this is repelled from the repeller, it's going to go through the focusing plates. We're going to get a nice tight beam. We're going to make sure all of the ions have the same kinetic energy as they then head to the mass analyzer. Okay, so that's our electron ionization source, and it's one of the most common sources, again, because of the reproducible fragmentation and the amount of information you can get from the ionization or from the fragmentation during ionization.